Yep. Yes. So you do have a few minutes
Okay.
of reprieve. Okay. Okay, so just by way of announcements, lab exam today. Just to kind of remind you guys, that's going to be during the lab. The format obviously will be practical, right? So there'll be station setup, questions, it's all multiple choice. Each station will be timed, so you'll have 2 minutes, 30 seconds per station, which is a lot of time, depending on the question set. For the questions that take a little more processing, oftentimes they're duplicated. So you'll have another 2:30 to work on them. Once we go through all of the stations, then we're done, basically, and you're free, at least you're from your obligations for lab. Now, on the lecture side of things, obviously on the 4th, which is next week, is going to be lecture exam 4. Now it's going to cover 12, 14, and 15. So we got work to do. All right. Okay, so let's do it. So as we were left off, right? So we basically are talking about Hershey Chase, and remember, just to kind of refresh your memory, Hershey Chase is basically trying to determine the difference between the genetic material as either DNA or protein, and so the system that they chose was bacteriophage, which basically is only made of protein and only made of DNA, right? And so what they did was they employed radioactive isotopes to highlight specifically DNA or to highlight specifically protein. Now, here's what they were looking at, right? So one of the things they knew was there was a phenotype to follow, right? So the phenotype that they were looking at was infection. So they knew that that phenotype was inside the cell. What that basically means then is driving that phenotype must have been the genetic material. So the idea is the genetic material had to have gotten inside. What they didn't know was what was it, right? Was it protein going inside or was it DNA going inside? That's what this experiment is trying to discern. So what they first did was basically take S35, which is a highlighter for protein, right? Because that's going to radioactively label all of your cysteines, amino acids, which are incorporated in proteins. And so here you can see basically they highlighted all of the protein portions of this particular bacteriophage. So they infected the bacteria. They let the bacteriophage kind of do its thing. But before the bacteria lysed, right, that is before it popped open and released a bunch of other bacteriophage, what they did was they blended it, right? Basically in a very high-tech instrument that kind of is about a Walmart brand, right? Kind of a Walmart level blender. I mean, pretty simple, low-tech stuff here. And what this did was, first of all, it kicked all the bacteriophage off and it kind of chopped them all up into little bits, right? Because they're on the outside. However, the bacteria itself were not harmed, right? So they were still intact. So the cells are intact, but not the phage. Not only that, but the bacteriophage are really, really tiny, right? So the idea here then is if we can separate this, can we determine what's inside? So then what they did was they basically centrifuged it. So centrifuging is essentially not unlike your rinse cycle on your washing machine. Basically, you just spin it around. All the heavy stuff goes to the bottom. All the light stuff stays up in the solution. That solution has a name to it. It's called the supernatant. And of course, then if your cells are down here in the pellet, then what you have is separation of your label, right? The question is this: what is in the cells, right? Is it protein or is it DNA? So what they saw in this first piece is they saw that the label was not inside the cells. It was in the supernatant. And where do we know the genetic material has to be? It has to be inside the cells. So what does this result suggest? No, not yet. That is, and that's, I'm glad you said that, because that is the most common mistake that researchers make. In this first experiment, they're not saying anything about DNA. Exactly. The first part of it is that protein is not the genetic material. That's not the same as saying the DNA is. That's a mistake that scientists make very commonly, and which is one of the reasons why I always say maintain your objectivity, consider all of your alternative explanations, and never fall in love with your idea. So somebody coming into this experiment who's in love with the idea of their opinion, then what they're likely going to do is jump straight to that, right? They're going to say like, aha, here we go. This proves that DNA is a genetic material. No, it doesn't. Scientifically, it proves nothing about DNA because you're not asking any questions at this particular point about DNA. The questions you're asking are about protein. It can only tell you about protein. You're inferring, and inferences can be wrong. DNA is a genetic material, right? Because that's the only one left standing. So here's the alternative explanation for that. In this first experiment, when you say protein is not the genetic material, you assume that that means that DNA is. But that would be a wrong assumption because it's not tested, right? It could be anything else. It could be some other molecule that you haven't considered, right? There could be something else out there that could be the genetic material. This is probably the most common mistake, and you see this actually a lot in research, which is the reason why we're very critical of each other. We look for things like this to pounce on each other, because this is a very, very common and a very easy mistake to make, because we're only human. We do fall in love with our idea. We do think we have the right answer. And so it's a natural impulse to say, okay, we're going to cut straight to the chase and we're going to say, this is it. But it's not it yet, is it? Because you can't prove a positive conclusion with negative data, right? You can't prove the non-existence of something by saying it's not there. You have to positively prove its absence, which is impossible to do, right? This is the reason why atheists and theists go round and round like dogs chasing their tail. They'll never finish that debate ever, as long as there's people alive on the planet, because that idea is fundamentally unprovable, right? And to conclude on negative data is not a conclusion, it's an assumption, and that's not scientific. So you have to follow it up. So this is what your principal investigator would say if you gave him this result and you say, look, DNA is a genetic material. You're a good principal investigator would be like, yeah, but you know what? You need to actually follow this up with a positive experiment that actually proves that DNA is it. Okay, let's do this then. Let's follow this up with a 232 label. Your case, you see you basically labeled your DNA, not the protein in this particular situation. You do the exact same protocol. You let it infect, and then you grind it up in your blender and you spin it down. And now, where is your label? Well, now your label is in the pellet. And what else is supposed to be in the pellet? The genetic material, right? Because that's where the infection is. So your DNA is inside the pellet where the genetic material is, where the infection is. So this one is the one that suggests that DNA is the genetic material, not the first one. Both of these experiments, and this is the reason why Hershey Chase is so great, because you need both of these in science. It's not sufficient to disprove something. You have to prove something else, right? So it's not good science to just disprove the guy you don't agree with. You have to prove yours, right? So just because you can set up a straw man, by the way, political scientists can do this too. And nobody would argue that they're brilliant by any stretch of the imagination, right? It's an easy thing to set up a straw man and knock it down, and you create the perception that you're right. We do it all the time. It's a delusion that we do in every political cycle. You know, we set up somebody to be like, hey, look, I'm not like this guy. Well, yeah, that's because you created this caricature of an evil villain, right? This, by the way, this is happening right now on the Republican Party side. You've got Trump, the evil straw man, which a lot of people don't like. A lot of people like him still, but a lot of people don't like. And what are they doing? They're positioning DeSantis as sort of like, hey, I'm not as bad as this guy, right? Therefore, I must be great. So they're doing the exact same thing that's happening now. Poli-sci people do this all the time. It's not good enough to disprove something. You have to prove something, okay? And so that's exactly what our Hershey Chase did. Yeah.
That DNA was the genetic material, and what did the people who thought it was protein thought DNA did?
They didn't know. They were basically reserving judgment. So they weren't quite sure what it did. Nobody really knew what it did, actually. That came much later. So Hershey Chase was 52. We didn't really understand how DNA worked until probably, well, we couldn't actually sit down and say, I think I understand DNA now, until probably the 70s. So it took a while. So the rest of this is basically review, and I'm going to move through it quickly. Okay, so we've already been through this in the macromolecules chapter, right? So we just refreshing your memory on DNA structure. So we know that we basically have a structure that's based on a 5-carbon sugar. In this case, it's deoxyribose with a phosphate group on it, on the 5' side of it, and one of 4 nitrogenous bases. And then the important thing is on that 3' side of the carbon is going to be a free OH group. Why is this important? Because this represents our growing end. Okay. So basically here is our nucleotide. So you can see your phosphate, your nitrogenous base. You can see your ribose sugar. Here is your 3' OH over here. This is your 5' phosphate over here. And then of course at the 2' position, you have an OH, which makes you either RNA, or a hydrogen, which makes you DNA, right? So this is going to be the deoxy version of ribose, and this is going to be ribose itself. Now let's take a look at the actual bases themselves, right? You have 2 families of bases. You have the purines, which are the double ring structures. And the way I remember these guys is the Purina double dog dish. So back in the day, Purina used to make those like little connected dog dishes. And so that's kind of what they look like. You had a big one connected to a little one. And so it's kind of like a little Purina double dog dish. And then you have the pyrimidines, which are single ring structures. Now, the important thing to understand this is when you're looking at these and you're struggling to kind of remember which ones are the purines, which are the pyrimidines, it happens all the time, right? It's very confusing. My genetics professor actually told me to remember this: pure, silver, taxi, which sounds really dumb, but guess what? I still remember it. By the way, my genetics professor is actually the author of the majors level genetics textbook now from Pearson, which was the book that he used back in the day, which is kind of cool. Mark Sanders. Just got to do a little shout out there to him. So I thought it was dumb. But at the time, we weren't that far displaced from the Back to the Future series, right? So you had the DeLorean. So the first thing I thought about was like a DeLorean, like picking me up from the airport. That'd be cool, right? That certainly beats Metro Cab and Yellow Cab. So that's kind of what I thought about, but this is basically how you remember it. You have purines. Well, pure stands for purine, and silver, what's the elemental symbol for silver? Ag, which stands for adenine and guanine. So the purines are Ag, silver. Now what's taxi? Taxi is a leftover, Tc, which are in this case the pyrimidines. Now, this is an important, the reason why we're breaking this down is because we want to take a look at this, and we want to basically sort of see some of these things like in terms of a chemical sort of perspective. So first of all, we already know a little bit of something about DNA. We already know it's a double strand, right? We already know that they zipper up together. We learned about that in chapter 4. But let's take a look at these actual bases and see if we can find potential fodder, if you will, for the production of hydrogen bonds, right? Because that's what's holding DNA together and your proteins as well, right? So remember when you looked at the backbone, you saw these electronegative atoms, which created the negative charge. And you saw all these sort of positive-ish hydrogens because they were attached to nitrogens, right? So if you recall back to your definition of hydrogen bond, and that's a long way to go, right? Remember, a definition of a hydrogen bond is an electrostatic interaction between the positive hydrogen of one molecule and the negative either oxygen or nitrogen of another. So the question is, let's find those. So, and this is what this is going to do. We're laying the groundwork for the relationships between these bases. So here you can see some hydrogens attached to nitrogen. So those are going to form some positive hydrogens there. Here's a nitrogen, which is electronegative. So that's going to form a negative there. This is also going to form a negative down here. Take a look at guanine. You got a negative on that oxygen. You got a really nice positive there hanging out there on that nitrogen, right? That nitrogen is going to be sucking those electrons off of that hydrogen, making it partially positive. You're going to see a partial positive on this hydrogen over here as well. There's a little bit of a negative down there on that electronegative nitrogen. you take a look at the pyrimidines, let's take a look at these guys. So these hydrogens are going to have a little bit of a positive personality to them. This nitrogen, because of electronegativity, is going to have a negative aspect to it. So there's this oxygen, right? That's a double bond oxygen sitting out there. That's going to have a negative aspect to it. And this hydrogen down here is going to have a positive personality to it, right? So we're just talking about electronegativity, and we're talking about that polarization of the bond associated with those imbalances in electronegativity, right? This is basically chapter 2 material, okay? So here you can see you've got a partially negative oxygen over here, a positive on your hydrogen there because all those electrons are being sucked in by the nitrogen, a little negative on your oxygen, a little positive there. Same thing happening with the uracil, right? So you kind of have a little positive, negative, and a little positive down here because the nitrogen is sucking the electrons off of that hydrogen. So basically what is this doing? This is basically forming the foundation for creating hydrogen bonds. Okay. Now, it doesn't necessarily mean all these are involved in hydrogen bonds. It just sort of is, we're sketching out the realities of these molecules to see if we've got a scenario by which we can form hydrogen bonds. And certainly we have plenty of options here. Right? There's a lot of positives and negatives associated with polarities. So this basically is your nucleotide. Your 3' OH, this is your 5' phosphate here, and of course we're linking your 2 nucleotides together with your phosphodiester bond. I don't want to beat the phosphodiester bond up too much because we already covered that in chapter 4. But the idea is, remember, because of the nature of your growing end, you can only grow in your 5' to 3' orientation. That's the only way you can go. You can't add anything up here to the 5' side because you don't have gallons of water. Remember, when you're building these, you're going through dehydration synthesis. And remember, dehydration synthesis requires the components of water, right? So you need a hydrogen on one and you need an OH on the other. So that's where this OH comes from on the 3' side. That's your OH. It goes in dehydration. So that's what requires you to add your new nucleotide to this end, to the growing end. You can only grow in this direction. So there's a directionality to all of this. Now, this brings us to Chargaff. Now, what we have basically is kind of in a lead up to essentially the discovery of the DNA molecule. A lot of pieces that were kind of locking into place. There's a lot of people that worked on this that kind of added bits and pieces to this. So as a matter of fact, any kind of discovery is a lot kind of like a community puzzle. You know, you lay a good puzzle out in the break room, and people have a break. They're just sort of, you know, decompressing a little bit. They can work a few pieces and then they move on, right? And so it's kind of a community project. These represent some of the people who added some of those pieces to the puzzle, some important pieces that we needed in order to be able to discover and figure out the actual structure of DNA. So the one thing that Chargaff noticed was that basically there's an equal proportion of purines to pyrimidines. That way basically means that the number of purines you had is equal to the number of pyrimidines. Matter of fact, what he also noticed was that the number of adenines that he found were equal to the number of thymines. Not only that, but he also noticed that the number of cytosines is also equal to the number of guanines. So if I have 50 adenines, how many thymines do I have? Right? So it's an equal number. Now, what we later figured out was because of all these little hydrostatic polarizations, right? These little negative charges and positive charges on the bases. What we now notice is that basically Chargaff is largely credited with discovering complementarity of the bases. So what we now know is that every adenine, the reason why there's an equal number of adenines and thymines is because for every adenine, an adenine will actually form 2 hydrogen bonds with a thymine. Not only that, but a cytosine will form 3 hydrogen bonds with a guanine. These two together is what we refer to as a base pair. So when you guys were doing electrophoresis and you were doing those DNA fragments, some of them were small, maybe 50 base pairs, some of them were big, maybe thousands of base pairs. Those base pairs are these little pairings, and it represents one strand of the double-stranded DNA and the other strand. So this was a very, very important discovery because it told us a lot about the relationship of these bases to each other. Okay. So we didn't really see that anywhere else. So this was a really key piece to the puzzle of solving DNA structure. Another key piece to the puzzle of solving DNA structure was a discovery that was made earlier by a guy by the name of Linus Pauling, who was a really smart guy, crazy as a loon at the end. He thought that you could cure cancer with vitamin C. Not really quite that easy, but that's okay. You know, we love him anyway. But Linus Pauling won the Nobel Prize not once, but twice. The first time he won it was for the discovery of the alpha helix. So the double secondary structure frame in proteins. So what he did was he worked on the structure of alpha helix. He figured that out, and that's what he won his Nobel Prize for. So at this particular time in the 40s, 50s, Linus Pauling would be considered like the expert on all things helix. Okay, so if you want to know about helix and what structural helixes look like and how they behave, Linus Pauling was the guy, right? So he was, and the second Nobel that he won was for peace, because he was an ardent anti-nuclear proliferation guy at a time when it was dangerous to be so. People went to jail because they thought you were communists if you had views like that. So, because Rosalind is the star of the show. Thing, right? Linus Pauling discovered alpha helix, but remember, alpha helix is just a single helix. So what Rosalind Franklin did is he was working on what's called X-ray diffraction studies. And so the way X-ray diffraction works is you take a pure molecule, in this case like DNA, and you blast X-rays at it, and then you collect the scatter pattern on the other side. So it's not unlike, you know, trying to study who you are, your structure, by looking at your silhouette, right? And so basically the way you diffract or bend the radiation, in this case, X-ray radiation, is proportional to your structure. Just like the way that you bend the light or block the light in the case of your silhouette is proportional to your structure. So I can tell a lot about your structure based on your silhouette. And that's exactly what you had here. So the first thing that we noticed from Rosalind's X-ray diffraction is that DNA is a helix. But it wasn't an easy one, because if it was a single helix, then Linus Pauling would have gotten it like that. It was a little unusual. It didn't behave like a normal helix. It didn't behave the way Linus Pauling saw with alpha helix. So it was very questionable, right? Because at this point, we didn't realize it was a double helix. We didn't know that such a thing existed. So what Rosalind then did, she kind of picked some vital sets. We knew it was helical. We didn't understand why it looked so different, strange from alpha helix. But if you were to basically, so what Rosalind did, she collected some vital data on this helix. For instance, she determined that the helix had a diameter of 2 nanometers and that it completed one helical turn in every 3.4 nanometers. So those were important pieces. She also discovered what's called major and minor groove in DNA. So she was actually able to discover a lot about the overall topology of the way the DNA molecule looked. So if you were to basically freeze frame this particular moment right here, you would say that leading the race to the structure of DNA discovery would clearly be Linus Pauling, because he was the standing guru of all things helix. DNA was a helix, and close to him was Rosalind Franklin, who was creating and defining the helical structure. He was using diffraction, but it was for proteins. So that's why he was definitely the leader in this chase, in this race. By the way, if he had actually done this, he would have gotten an unprecedented third Nobel Prize, probably, because everybody knew that, right? At this particular point in this era, everybody knew the person who discovers the structure of DNA is going to win the Nobel Prize. That's the reason why it was such a hot, contested race. It was pretty shameless, actually. Well, we're going to talk about that. So now I'm glad you said that, because who ended up winning the Nobel Prize? I wish. Jared. Keeping him honest, Jared. I see how that's going. This is probably one of the more famous pictures in scientific lore, unfortunately. These are the guys who get all the credit. How do you guys feel about that? So here's how it goes. Clearly, I've got an opinion. Have you ever seen me draw devil horns on anybody else? And basically expunge them from history? We'd be better for it, actually, if we expunge their names from all of history, the way the Egyptians used to do when they didn't like a pharaoh. Just basically chisel out their name. That's what I feel like we should do. Here's what happened. There's a couple of different versions of the story. The more aggressive ones basically have Watson and Crick moseying down the hallway and taking a look at Rosalind Franklin's data, from which then they basically unlock the structure of DNA, which is this. And then what do? They go to the presses. We've discovered the structure of DNA. Aren't we great? And as usual, and this was the first time this actually happened, right? I mean, this was met with great fanfare. These guys were like rock stars and celebrities. Everybody around the world was like, oh my gosh, Watson and Crick discovered DNA. This is like a momentous, point in human history. I mean, it was absolute celebrity for them. They wrote books. They wrote all kinds of books. They gave interviews. I mean, it was like a rock star tour. Everybody wanted to talk to them. I mean, it was just an absolute nauseating infatuation. And of course, there they are, two peacocks strutting around. Look at me. I did it. I solved the structure. Really? Last time I checked, you were too damn stupid to actually solve the problem yourself. Not only that, but you didn't do a single damn experiment. You freaking losers. Your names should be expunged from history. Oh, it's worse than that. The softer versions go like this. Well, it's not really that bad. I mean, it was more of a collaboration. So, I mean, they came by the data, honestly, because they were collaborating with, in this case, Maurice Wilkins' lab, for whom Rosalind worked for. And it was an honest collaboration. And then they didn't do anything wrong. They just basically got all the notoriety. And so that wasn't a problem. It doesn't really matter, because what happened next was unforgivable in any stretch of the imagination. While Watson and Crick catapulted to stardom and celebrity, guess what happened to Rosalind? She got trashed. Completely classic male chauvinistic burial. I mean, like, really galling. I mean, they basically just eviscerated her. So not only did they say, look at me, proud white male privilege, I own the world, but then they basically sandbagged and annihilated Rosalind Franklin. So that was, and I don't say this lightly, but in science, that fostered generational anger, like unlike anything. And to this day, the anger is still visceral. Generations of researchers coming up in universities after this, by the way, a lot of these generations were coming up during the era when the ERA was gaining steam in the 70s. So there was a lot of women's lib stuff going on. And then Rosalind Franklin was sort of like the poster of like, this is what these stupid white men do, right? They take somebody, a woman who's smarter than they are, and they bury her. That's what they do, right? And so every generation since then has been flaming angry, which is the reason why Rosalind is in every single textbook. And just about every single professor will have a similar discussion when they hit this particular section. Some are more heated than others. For me, it pisses me off because some of the most brilliant researchers that I ever worked for were women. And we're doing better at recognizing them now, but it only came because generations were screaming angry, about ready to strangle because of this. The Nobel Prize can be shared by 3 people. And that's it. Who were those 3 people, do you think? Obviously Watson and Crick, right? But who was the third? It was Maurice. They didn't give it to Rosalind, they gave it to Maurice. Now, no knock on Maurice. I mean, he's just the guy who he was just the principal investigator of the lab, right? So, I mean, he didn't necessarily do anything wrong. And this is kind of like Watson and Crick's defense. It's like, when we didn't do anything wrong, Rosalind didn't own the lab, Maurice did. So Rosalind was a postdoc, Maurice owns the data. That's kind of the understanding in scientific culture. But that wasn't the point. The point was that credit was not given where credit was due. Here's what Watson and Crick did. They committed 3 cardinal violations in scientific research that you never, ever do. Number 1 is you never steal somebody else's data, ever. You might as well tie a noose around your neck and kick your own chair out from underneath you, right? That is an absolute no-no. Number 2 is you always give credit where credit is due. Always. And then number 3 is you always deprecate and defer to the industry at large. Right now, and they didn't do any of that. Here's what they did. Remember the communal puzzle? What Watson and Crick literally did was they basically came in and took the last piece. They're like, look, I just solved this whole puzzle. Look at this. No, you didn't. A trained monkey, actually an untrained monkey, could have solved that puzzle. So Watson and Crick were among the stupidest researchers that were ever awarded the Nobel Prize. Actually, as a matter of fact, Watson has a notorious reputation of being an absolutely aggressive racist. He was actually fired from institutions for being a racist. Crick now went on to make some important discoveries, but largely, listen, I mean, if you're associated with an a-hole like Watson, sorry, that's a bad judgment call right there. Okay, Christopher.
When they present these the Nobel Prizes, do they investigate to providing this sound and point where you come out with the most groundbreaking?
No, they used to do that. They don't do that anymore. What they do now is they kind of leave it up to the robust peer review thing. Here's what happened. This has happened a couple of times. When it's happened, none of these Nobel Prize winners have been popular. The guy who invented PCR basically got the Nobel Prize for the importance of PCR, but that's literally all he did. He invented PCR and then he went and smoked marijuana and surfed in California. That's basically what he did. And everybody hated that, right? That's the third, by the way. That's actually the third cardinal rule, is you put your dues in. Right now, what happens is people have less concern about who wins the Nobel Prize. Because what happens is when you take a look at it, you've noticed they don't get the Nobel Prize until it's like decades of work have accumulated. And not only that, but there's less angst there, right? Because you have competing labs. It's like, yeah, it sucks that you got it and I didn't. But you know what? We've been kind of digging this hole. We've been sweating in this trench together. working together. And I have no problem with this because I know you've been there for decades doing the hard work, right? So there's a sense of like, you've earned the right to be considered for the Nobel Prize. They earned nothing. They took all of the work of decades of important people who were more important than them, and they basically stole their credit and their prize, and then they expect us not to do this to them. My former PI, Tom Blumenthal, actually worked in the lab of Jim Watson. And he never really said anything one way or the other about Watson. It's like one of those things where you can't say anything good, don't say anything at all. I mean, there's probably some defenders for Watson and Crick, but I can guarantee you there's probably many, many more anger, much more anger than not. Especially now when we're really trying to sort of figure out this whole equity and structural racism thing. And we look at this, and what you see is basically a flagrant, like an obvious violation of white male privilege. And that really resonates. And it's like, it's visceral. It's always been visceral. It still is. And I would say the arguments now are even more heated than they were in the past. No, you can't take them away. And actually, they probably would have awarded Rosalind because of such anger. It's awarded by the Swedes. And I mean, the Swedes are soft, right? So they don't want anybody to be angry at them. So probably they would have awarded Rosalind the Nobel Prize, but she died. So I think she got cancer or something like that and died. And so actually, I think since Marie Curie, I think one of the women at the same time that finally got the Nobel Prize was Barbara McClintock. She got it when she's like 83, and actually in the 80s, early 80s when she got it. But that was because of this anger, this burgeoning. It was almost like a volcanic buildup of anger. And finally, the Swedes got the idea. It's like, oh, yeah, we probably better start taking a look at some of these brilliant women that are making all these discoveries. Barbara McClintock, by the way, I loved her story. She's a genetics person, which I'm sure you guys will hear plenty about when you take the genetics class in the fall. Just kidding. Not really though. It's always shameless. I have no problem with that one. Right, but basically Barbara McClintock was a geneticist, and actually my former PI at UC Davis, Scott Hawley, who's now in the Academy of Sciences, he actually knew her. And he had all sorts of great stories about Barbara. She was a corn person, so she's a corn geneticist, and he would say that she could walk through a field of corn and she could just look at the corn and tell you exactly what's happening to that corn genetically. And I mean, it was just amazing how brilliant this woman was. She could think circles out of any of her male colleagues there. And this was true for decades. Anybody in genetics knew. It's like Barbara McClintock is like the top. I mean, she is like Mendel's forebears. Like she's the one who took the standard from Mendel. She is the top geneticist, but they didn't give her the Nobel Prize until she's like freaking 83 years old. And that's mostly because we got so angry over the Rosalind Franklin slight that it's like, okay, we're going to start recognizing some brilliant women. Oh, Barbara's an easy one. Everybody agreed about that one. Nobody argued about that one. I mean, when she got that one, everybody was like, yeah, Barbara, we have been like, you know, bowing to her for decades. It's nice that you guys finally woke up and figured this out. Now we're doing much better these days, but we still have a ways to go. Right. His name is Kerry Mullis. Nobody likes him.
What is that just because of
Nice. Thank you, Jared. Life coach right over here, Jared.
because of the fact that, I mean, I could understand his perspective being like, oh, like where I got money coming in. Well, because I know that like their point, how many won that? It's like you need having to like the most groundbreaking.
Yeah, he got it like very quickly too. Part of the reason why they didn't like him was because he was like a postdoc or something like that. I mean, he violated the third rule. He didn't put in his dues. So what he created was a really, really fantastic mechanism in PCR. Nobody doubts that, right? But there was a lot of people who were already doing kind of PCR. They would have to do it with water baths and do the temperature thing. And what he did was basically he figured out how to upscale it. And so they gave him the Nobel Prize, but it's like his violation was like, wait a minute, but you haven't really done anything. Yeah, you kind of invented this sort of streamlined version of PCR, which we've known about since the 70s, by the way. He got it in the 80s, the late 80s. And this is what you've done with it. And not only that, but then after you get the prize, you bolt. So it's like you're totally, that's a total violation of sort of the scientific ethic. I mean, you didn't put in any of your dues. You didn't really do hardly any of the work. You got all the reward. The reason why people don't like Gary Mullis is because they remind them of Watson and Crick. And what we really want to do is we want to punch Watson and Crick in the face. But anyway, so here's our DNA molecule, right? So a couple of things I want to point out here. First of all, you notice that you got your backbone, you got your 5' phosphate over here, your 3' OH over here. So you've got your sugar phosphate backbone here. And then of course, on the outside, you got basically sticking out your nitrogenous bases. Now, one of the things that I want to point out is that whenever you have a DNA molecule and you draw one strand, so we have 5' over here, 3' over here, I'm going to put in a couple of bases. So let's do A, C, G, A, T, A, C. Then on this side, we're going to have our complements, which are going to be what? A goes with T, and it forms two bonds, hydrogen bonds. C goes with G, and it forms 3. G goes with, and it forms 3. A goes with, and it forms 2. Of course, A goes with T. A goes with T with 2 double bonds or 2 hydrogen bonds, and of course we have GC with 3. What's the complement to 5'? 3, right? So notice what happens is basically you have an anti-parallel situation. You have 5' to 3' going one direction on one strand, 5' to 3' going the opposite direction on the other strand. So you have a northbound and southbound freeway. So that's called the anti-parallel aspect. So if you're reading, you can only read in one direction on one strand. Okay, so you have to turn yourself around and read the other strand. Now that becomes important later on. So here's our DNA molecule. You can see Rosin's contribution, which are 2 nanometer diameter and our 0.34 nanometer helical card. Also, you notice there's a minor and a major groove in this molecule itself. And of course, you can see Chargaff basically sets down those complementary relationships in between. So again, I ask you, what really did Watson and Crick do? Pretty much all the data is there, isn't it? Which is the reason why the authors of this book, very diplomatically, pretty much make a bullet. They did not perform a single experiment themselves. They violated every cardinal rule of science. Yeah, you do all the work, somebody else gets all the credit. Nobody enjoys that one, right? Okay, let's take a closer look at these. So the actual hydrogen bonds they do make. So this particular oxygen, which is negative, is going to form a hydrogen bond with this positive hydrogen. This positive hydrogen is going to form a negative, kind of a bond, a hydrogen bond with that sort of negative nitrogen. This hydrogen has a slight positive to this negative on this oxygen. That's going to form a hydrogen bond. So there's your 3 hydrogen bonds between C and G. Between A and C, this positive hydrogen is going to see this negative oxygen. So that's going to form one hydrogen bond. The other one is going to be formed between this negative nitrogen, this positive hydrogen. Now, a lot of times students will be like, wait a minute, what about this one over here? Isn't there a negative on this oxygen over here and a negative on here and a slight positive over here? Well, not really, because this atom right here is carbon, not nitrogen. Carbon doesn't have quite the electronegativity that nitrogen does. So this really isn't a very strong positive charge. Not only that, even if it was, the distance here is actually too far apart. So basically you can't form that hydrogen bond because it's just too far apart. Okay. Okay, so let's take a look at our models of replication. So we take a look at the mechanism of replication. We have 3 basic models that we look at. The first one is called the conservative model. In this particular case, what's happening is you have your parental duplex, or your 2 strands of the DNA, will remain intact. What this basically means is you essentially make the new strand from scratch. Now, here's the problem, right? Where's the information? To make the new strand. If you're making it from scratch, you have to have information. Right now, there's nothing, right? The old strand is just hanging out there doing its thing. So where do you get the new information from? Right, so what you're asking for is making a new molecule from scratch with no information to inform you, which is essentially like a recapitulation of evolution. Right, so the idea is if it took a ridiculously long time for this original DNA molecule to come together, then it's going to take a ridiculously long time for this new molecule to come together. And that's happening not just once, but that's happening every single time you go through mitosis. How many times have you gone through mitosis at this point? A lot. Is it practical to expect a reinvention of DNA every single mitotic round? No, it's preposterous, right? So just thinking this one through should eliminate this one. And there's semi-conservative model. What this basically means is that one parent duplex remains intact, but the other forms a template. So this is essentially the old DNA. Forms a template for the new. And then the last one is dispersive, is kind of a mixture of old and new strands, kind of like a quilt, right? So you have patches, like they're patchwork. So kind of what it looks like. So you conservative model, you see basically you just essentially made your new from scratch. Your old is still there. You haven't changed your old. You just made your new from scratch. And semi-conservative, you can see that basically you have a new old hybrid where the old was used to inform the new. So you just basically made a copy of the old. And the dispersive is kind of like an old new mixture, but it's kind of like all over the place. It's like little patches and chunks kind of peppered throughout. This one is considerably different. So then we get to Mendelssohn-Stahl, which is another really important experiment that happened in 1958. So just to kind of give you a little bit of context, I always love history, right? So it's at 1958, basically Eisenhower is coming to the end of his tenure. This was the last 2 years. He ended in 60. And he was going through his midterms, got reelected in 56, so he's kind of coming to the end of it. His vice president at this time is one Richard Nixon, who would later, 10 years afterward, become our president. Crash and burn in infamy. Yes.
I heard this last night, actually. Have you ever heard about Nixon and Jackie Gleason, their UFO experience?
No.
Well, I'll tell you.
So that's basically in the middle of the 50s, right? So this is kind of an important thing because this actually marks a watershed in American history. If you're looking at near American history, in 58, in the 50s, right? This is the Leave It to Beaver era. This is the era of the Red Scare. This is the era where you can't really claim to be an outright liberal because they think you're a communist and throw you in jail. That actually happened. I mean, McCarthy was a senator who was on a witch hunt to basically apprehend. I mean, the Hollywood stars were dealing with this a lot. This is one of the things that Lucy, actually of I Love Lucy fame, had to deal with because she was an actual communist. I mean, she was actually a registered communist, which wasn't a bad thing. It was just, you did it, right? It was a thing you did in the 20s. And so that came together. But that's what was happening here, right? This is the Leave It to Beaver era. This is kind of like the ultimate American repression thing. But it was an important thing because Eisenhower did his job. He did what we needed him to do, which was essentially provide stability for the country so that we can heal our wounds post-war. By the way, Europe was doing the same thing. They were rebuilding under the Marshall Plan, under our guidance. Marshall was actually the Secretary of State for Eisenhower. That's where that Marshall Plan came from. And so the important thing here, the watershed is here, is in 1958, there was a young man from Massachusetts who was a relatively new senator. And his name was John F. Kennedy. So JFK was a senator at this point, probably gearing up to run in 60, which he did against Nixon, and he won. A lot of people think he slam dunked Nixon. He did not. That election was a very close one. but he won. And Kennedy, the reason why Kennedy is important is because Kennedy basically marks the sort of the before and after, right? So the way America was had one reality before Kennedy and after Kennedy, and especially the assassination of Kennedy, the reality of America was completely different. I mean, we literally walked through the looking glass with Kennedy, and the America of the 60s resembled nothing of the America of the 50s. It really was a before and after moment. And so that's basically what was happening in Messis and Stahl. So what they wanted to do was differentiate between these three mechanisms. And the biggest problem they had was basically, okay, this is fine. I want to differentiate between these three mechanisms, but how do I do that, right? In order to do that, I got to be able to differentiate between an old strand and a new strand of DNA. But how do I do that? Because it all looks the same. It's all just nucleic acid. So how do I differentiate between old strand and new strand? Well, what they did was something rather clever. So what they did was they took bacteria, because that's what they worked with. It was a simple system and we knew it well. And they basically gave bacteria an isotope of nitrogen, or nitrogen's normal mass is 14. And so they gave bacteria heavy nitrogen. And it has an extra isotope in it, right? It has an extra, excuse me, not an extra isotope, it has an extra neutron in it, right? That's why it's 15 instead of 14. And then what they did was they allowed the bacteria to grow in this heavy nitrogen. So what that means is when the nitrogen were building all of their bases, adenine, guanine, cytosine, those nitrogens that were in those bases, they were using the heavy nitrogen. So they're incorporating heavy nitrogen in everything they did. And so over time, then everything, all their DNA became riddled and permeated with heavy nitrogen. Then what they did was they switched it to normal nitrogen, which is lighter. And then they basically sent bacteria through 2 rounds of replication. Now, when you switch it to light nitrogen, then when you go through replication, you're making new DNA. The new DNA is going to be pulling from the normal nitrogen. So the new strand is going to be lighter than the old strand, which is nitrogen 15. So this is the way they differentiated between new and old. So basically, between the three, you have 3 basic outcomes. Let's go ahead and lay down our predictions and see what we should expect. From the conservative. So basically what's going to happen is you're going to have your first round of replication and your second round of replication. So after the first round of replication, you're going to have an old strand and a new strand. But remember, the old strand is heavy because it has heavy nitrogen in it, right? So you would expect, if you run this out on a gel, to have a heavy band and a light band after the first round of replication. But now, what's going to happen if you go through a second round of replication? Well, this is going to be new, and this is going to be new, and then you're going to maintain the old, right? So here you would expect the light band to get darker, and the heavy band is slowly going to start to disappear. That's what you would predict if it were conservative. What if it were semi-conservative? So you'd have heavy, you'd have light, but now what's going to happen is you got a combination in between, right? So you have these hybrid molecules, which are a mixture of old and new. Light, they're a little heavier than light because of the old strand, but they're a little lighter than the old because of the light strand. So what you would have is you would have a medium size. So this is what you would have. Now, what happens if you send it through a second round? Well, these guys would replicate. So if you took this strand right here, it would create a new. This one would create an old new. So that'd be your intermediate, right? This one do the same thing, right? New, and then old, new. So now what happens is in the second one, you would expect intermediate, and you expect the light band to show up now, right? Because now you've got new, right? Or the light band. Now for dispersive, we're quite sure what they were thinking here. So for this one, you would think that after the first round, you would have medium, one band, right? So it'd look like the semi-conservative. But what would happen? So what would happen is you'd continue the same, wouldn't you? So you'd kind of continue this sort of medium. You just basically recapitulate what you've got. And so you'd expect something like this. So now you can see you've got 3 different patterns. All you have to do is do the experiment and then see which one is consistent with your results. So what they see? They did not see after round 1 the 2 densities. So they rejected conservative. For the what they saw was 1 band after 1 and 2 after 2. So they also saw that's also consistent, by the way, with dispersive. So in the first round, it's consistent, but in the second round, you stick with 1 band in the dispersive, but they saw 2. So that basically rejects the dispersive. So the first round eliminates the conservative. The second round eliminates the dispersive. The only one you have standing is semi-conservative. And this is their data. So here basically they do their incubations on heavy nitrogen and then they switch it to light. And then they let it go for the first round. And then they let it go for the second round and then they analyze it. So here's what they saw. So before replication, they saw only a heavy band. That's what this was here right here. And then after the first one, they saw the intermediate band, right? That's because you got your hybrid. And that's, they see a little bit of a shift there. And then after the second round, they see now the appearance of the light band and the intermediate band. So that's the light and the intermediate. So the results are actually consistent with the semi-conservative model. That is to say that DNA forms information. Okay. Replication isn't necessarily unlike just making a photocopy. There's 3 things I need to do in order to make a photocopy for quiz. What do I need? I need the original, right? What else? Paper and the printer. So the printer is the actual structure that does the copying. The paper, and I'd put the toner in that as well, is the materials that the printer needs in order to make the copy. So I need those 3 things. Same thing's also true for DNA. So first of all, you need something to copy, right? This is your template. Sorry, conservative people, not happening, right? So you need something to copy. Then you need something to do the copying. These are the enzymes of replication that will actually do the structural component of copying. And then of course you need the materials in order to actually build the copies itself. These are the nucleotides. Okay. So you need all 3 of those. Now, a 3-step mechanism, and this is an important one to remember, right? Because this is absolutely true, not just for DNA replication, but it's also true for transcription and translation, which are going to be the next chapter. So all of these basically have a 3-step mechanism. There are events of initiation, basically getting everything together before you actually start the process. And in each one of these, we have different initiation tasks that are associated with. So most of what we talk about are the details of the events that are happening, either in initiation, elongation, or in termination. The next one is elongation, right? So once you get everything set up, you get the table set, then you actually do the job. You actually perform the task of, in this case, putting together DNA. So that's elongation. And then, of course, all good things have to come to an end. And so you have a method or a mechanism to stop, right? So that is basically your termination. So this is true for all of them. For the next 2 chapters, remember that. Initiation, elongation, termination. Okay. Now each one has different tabs. So here's basically what happens. So here's basically our template strand up here. So this is what we're reading off. And we have an enzyme in this particular case, the first one of our cast of characters that are involved in replication, which is DNA polymerase 3. What DNA polymerase 3 will do is basically it'll sit down right here and it'll read off the template. So it reads off an A, says, hey, I know what goes with A. What? A T, right? So what it does then is it grabs a thymine nucleotide. It'll pull off these 2 phosphates. That'll leave as what's called pyrophosphate. And then it'll form the bond between the phosphate and the backbone. That locks the T into place where you can form your 2 hydrogen bonds between the A and the T. Then what it does is it basically reads the next one in line. Oh, hey, there's another A there. So what do I grab? A T, and I do the exact same process. So DNA pol 3 is an enzyme whose job it is to basically build the nucleic acid, and it's building it by the dehydration synthesis process. That's the mechanism by which it's building, okay? Which is one of the reasons why that discussion about dehydration synthesis and hydrolysis is one of the more important discussions that we have in the semester because it informs everything we do for the rest of the semester for the most part. Okay, let's take a closer look at the polymerase. So DNA polymerase itself basically is the one who's going to be reading off the template and putting that nucleotide into place. So here's your DNA polymerase here. However, there's a couple of features of the polymerase which limits it and defines it. Number one is it can only add new bases to the 3' growing end. Why? Because you need that 3' OH for dehydration. What does that mean? That means it can only synthesize in the 5' to 3' direction. Can't go backwards. Yeah.
And this is like the DNA.
This is the DNA polymerase we're talking about.
Well, yeah, when it's not the DNA, but hereditary, 3, 3, 1 of those.
For DNA, yes. Yep. So here's the problem. The other thing as well, polymerase cannot self-start. That's one of its limitations. So when it sees wide open template, it's just looking at it bewildered. It's like, okay, wait a minute. What do I do with this? I need a 3' OH, but I don't have one, do I? So where am I going to get my first 3' OH that I can grab onto and start building off of it? It can't lay it down from scratch, so it needs help. That basically means that we require a primer of RNA. So what is a primer? Well, basically this is a primer. It's a short stretch, typically, of RNA. And so here you can see you got 1, 2, 3, 4, just 5. You don't need a lot. But what this does is it basically provides a 3' OH. Once it does provide that, then the DNA polymerase is off to the races. It's like, okay, I got my 3' OH. I know what to do now. But it needs that primer. So who does that primer then? Well, as it turns out, it's a different polymerase, an RNA polymerase. RNA polymerases are distinguished differently from DNA polymerases in the sense that they can self-start. So an RNA polymerase does have the ability to lay down a nucleotide from scratch. So they can create this 3' OH for the DNA polymerase. So you need those two in order for this DNA polymerase to be able to do its job. So let's take a look at the prokaryotic background. I'm going to move through this quickly because we've already covered this through chapter 10, right? So we already know that the prokaryotic genome is a circular genome. We already know that they've got an origin of replication. We already know that they proceed in both directions. And so this is just a recapitulation of what we've already learned about in terms of replication in chapter 10. So that's kind of what it looks like. So basically, remember, you have both an origin of replication, which is your start site. This is basically a site on your DNA that says, hey, start your replication here. And then, of course, you have a termination site. So then your replosome is going to basically start replicating the genome and rolling both directions, counterclockwise and clockwise, until they both hit the termination site, at which point you'll have the magician's ring, the connected magician's ring stage. And then these will separate. And then when they separate, they'll be inside the cell. And then you basically go through cytokinesis. So that's kind of all review from chapter 10, the early part of chapter 10, when we talked about binary fission in bacteria. But this is basically how replication is understood, how we understand replication. You have an origin of replication. In the case of bacteria, you've got a termination point as well. Turns out you don't have a termination point at eukaryotes. That's for a different reason. We'll talk about that a little bit later. So when you take a look at DNA polymerases, right, these are, we already talked about one, Pol3, but there's actually 3 DNA polymerases that are in bacteria. The first one is actually, its job is to find these RNA primers that we laid down to get DNA Pol3 started, and it removes them and replaces them with DNA. So this is like a finisher. So Pol1's the finisher. It'll come in there, remove those RNA primers, and put down DNA. Remember, your DNA is not a patchwork of DNA and RNA. It's all DNA. So that means those RNA primers have to be removed and replaced with DNA. That's what Pol1 does. Pol2 is actually focused on DNA repair. So this basically will replace areas of DNA damage. So it'll find an area of DNA damage, cut it out, and it'll replace it. So it lays it down in there. And so then DNA Pol3, of course, is our main workhorse. So this is the main bulk creator of DNA, right? So this makes most of the DNA. Now, the important thing is that when you're talking about dehydration, so all of these have dehydration capacity. That is to say, they're putting stuff together, right? That is that dehydration synthesis capacity. And that's in a 5' 3' direction. However, what about the hydrolytic activity? Well, this is their hydrolytic activity. All these guys will have a reverse direction, a 3' to 5' exonuclease activity. So what does that mean? That basically means that if you have this right here, you've got a little exonuclease Pac-Man that can basically gobble up and chew off that 3' end. So that's something that all these polymerases can do. So this is a lot like a backspace button. So if you're typing an email and you flub up the word "the," which for some reason there's something about those 3 letters that I just cannot get right the first time around, sometimes the second or third. Yeah, right. What do? You just hit the backspace button, right, and you just retype it. That's exactly what this activity is. So the exonuclease activity is a situation where you flub up a matching or mismatch or something like that. You catch it, and then all you do is you basically use your exonuclease activity to backspace, and then you relay it down. Okay, that's what this is. Call 1 is the only one that has 5' to 3' exonuclease activity. So it can chew up in both directions. So for instance, if you have a 5' versus a 3', it's got a Pac-Man, an exonuclease on this end and on this end. So this is your backspace, but this here would be like your overstrike. So it can basically gobble you up going front or back. Okay. And that just makes it easier for it to be able to remove those primers. Either way. So when we take a look now, a couple more characters in this play, right? The first thing we have to do before we make DNA is we have to make the DNA available, right? So that's the first member of that party is called the helicase. The job of helicase is to unwind the DNA. So this is kind of like the unwind days. So it'll unwind the DNA, and what it'll do is it'll create something called a replication fork. And basically open up and expose your single-stranded template. And here's the problem. Single-stranded nucleic acid has one destiny in the cell. It gets degraded. So if you have single-stranded nucleic acid, that's a dangerous thing, especially with your DNA. You need to protect this because otherwise it's going to get degraded. So one of the things you have are proteins whose job it is to do just that. You bind single-stranded binding proteins on your single-stranded template. And what this does is basically it stabilizes and protects the template. So it protects it because it blocks that single strand from being degraded. Okay. And it stabilizes it because as soon as you open up that replication fork, that single strand, all it's going to want to do is just zipper right back up. Right. So if you basically unwind and separate that DNA and create the fork, as you move on, guess what's happening behind you? That template is just going to zipper right back up behind you. Right. So it's kind of like whack-a-mole. So wait a minute, I just unwound this one, but this one just wound right back up. So now I got to unwind this one, and this one's going to wind back up. So you're going to be maddening, right? So what you do is you have single-stranded binding proteins, which keeps the template unwound and protected. Now, during all this unwinding and winding, you're creating a lot of stress and strain. That's where our third member of the party comes into play, the topoisomerase. And what these guys will do is prevent supercoiling. Now, what supercoiling basically is this right here. So the best way to describe supercoiling is to take a rubber band and roll it between your fingers. What happens to the rubber band? Yeah, it kind of balls up, wads up, right? So that basically is like supercoiling. What you're doing is you're creating torsional strain in a closed system. And so the supercoiling is evidence of the increase of that torsional strain. So what do I need to do in order to relieve that torsional strain, assuming I'm hanging onto it? And I don't let go, right? If I take scissors and I cut the loop, what's going to happen to it? It releases that torsional strain, right? That's exactly what topoisomerase does. So basically what this does is it nicks the backbone of DNA. To relieve torsional strain. This way your DNA doesn't get all balled up. So you can imagine topoisomerase is going out ahead of the helicase, smoothing everything out by nicking it and relieving that torsional strain. Why? Because helicase is like twisting and untwisting and twisting and untwisting and that sort of thing. That's building up a lot of torsional strain in there. Okay. So that makes sure that everything gets all nice and smoothed out. So those are some major players. Then what we have in the mechanism of TNA. So we've already met a couple of players, right? So we've kind of met a couple of cast members of this whole plot. We've met Paul 3. That's the big boy. We've met Paul 1. That's another one. That's the finisher. We met helicase. We met single-stranded binding protein. We've also met topoisomerase, right? So we have 5 of them so far that we've been introduced to. We'll see what these guys are doing actually as we sort of explore the entire mechanism. But first of all, the mechanism of replication is what's referred to as semi-continuous. So instead of trying to explain what that means, let me explain what continuous looks like and versus what discontinuous looks like. So continuous basically means is that you get started and you move forward and you don't stop until you're done, right? So it's a continuous product. And so when you take a look at your replication fork, you create a primer here. And then basically what's going to happen is you're going to be moving in toward the replication fork, but all your new template is in front of you. So you just keep on going, keep on going, keep on going, right? That's what's called the leading strand. And it basically makes its nucleic acid continuously once that first primer is laid down. The problem is on the other side, since you have to go that direction, then what that means is if you lay down a primer here and you move in this direction, then the new primer is going to be behind you. But remember, you don't have a reverse gear. Right? So it's a little discontinuous. That means you have to break off and you have to sort of rejoin back here in order to make that new sequence, right? So it's kind of a little jerky, right? A little kind of, but what this does basically is it creates little fragments and pieces. So if you were to like take DNA and denature it at 96 degrees and run it out of a gel, you would have the main template strand and the new strand, but then you have all these little fragments, these little chunks and pieces that are associated with this lagging strand, this discontinuous process, which are called Okazaki fragments, right? These are like little chunks because you're basically making the DNA in batches, right? Like in little chunks instead of in one continuous strand. So because you have a leading strand on one side and a lagging strand on the other, we call it semi-discontinuous. It's not continuous all the way around, it's not discontinuous all the way around. It's one of each. Right? So that's why we call it semi-discontinuous in nature. This is kind of what it's like. So here you can see your initial primer here, providing your OH. Your polymerase will grab onto there, and then boom, it's off to the races, and it never stops until you run out of template. However, in this one, notice you form your first primer, and then you finish out your piece, but then your new sequence is now behind you. So here you are over here, and you're like, wait a minute, but my new primer is back over here, so I'm going to have to fall off and jump back here and then fill that in. And that's like a big gap. So that's like a big chunk or fragment. That's the Okazaki fragment. All right, so over here you have the lagging strand. On the side you have the leading strand, right, which is continuous in nature. So when we take a look at this, however, the first thing we need to do after we unwind, right, which is the helicase, first process is unwind with helicase, stabilize it with single-stranded binding proteins. Then what? Well, then the next piece is to prime the DNA, to create your RNA primer. So who does that? Well, it's an enzyme called DNA primase. This is number 6, cast member number 6, DNA primase. And DNA primase is actually a type of RNA polymerase. Remember, RNA polymerases have the capacity to lay down a primer from scratch. And that's exactly what it does. And so it's primase's job to lay down that RNA, that initial RNA primer, so that you can have what you need in order to get started as a DNA polymerase. So let's take a look at leading strand first of all, and then we're going to take a look at the mechanism of lagging strand and look at like everything all together. Now we got most of the cast members in play. When you take a look at, I don't know how long that's been up there. I apologize, Crystal. You've probably been there for most of the morning. Wondering if I'm ever gonna notice you. I did notice you, Crystal. Sorry. So if you take a look at the DNA pol 3, right? So after your priming event, then comes in polymerase. But one of the things that you see in the multiple subunits of the polymerase, but the beta subunits form something very interesting. They form what's called a sliding clamp to kind of keep it attached. And so this is kind of like your sliding clamp here. So here you can kind of see your clamp basically clamps onto the DNA and it basically slides along the DNA. So if you take a look at it, the sliding clamp will actually basically load onto the DNA like this, and then it basically will just slide along the DNA. That's why they call it the sliding clamp. Now, as it turns out, the clamp is also the main loader for the DNA polymerase, the bulk of the DNA polymerase enzyme. So really what happens is you've got the clamp, which clamps onto the DNA, and the polymerase, which clamps onto the clamp, and then the entire complex slides. We'll see that here in just a second. Once you load this up, once you attach your polymerase with the sliding clamp to your DNA, guess what? You're off to the races, right? So you're done pretty much. You just go and do your thing. It's all elongation at that point, right? So what about the lagging strand? This one's a little trickier, right? Because its mechanism is discontinuous. It still uses pol 3. That's still a thing, but it's going to be making multiple primers, not just one, right? Which is what causes those Okazaki fragments, by the way. And eventually they're going to be removed and replaced by pol 1. So we saw that mechanism of pol 1. And then who seals the backbone? DNA ligase. One of the important things to remember is that these polymerases, all they do is dehydration synthesis. Polymerases don't seal the backbone. So all it can do is basically run up to the last base in line and add that. It can't seal that last nick. So one thing that a DNA polymerase cannot do is come up to a piece like that and seal that nick, because it doesn't have that capacity. All it does is just basically add nucleotides. That's all it does. If it were to continue on, what it would do is it would basically continue adding bases like this. So it would do something crazy like that, which you don't want to do. Right. So what it does is it runs into that next piece and it stops and it leaves an open gap there. So who seals that nick? Ligase. This is the reason why it's not a big deal for topoisomerase to go ahead and nick the DNA to really torsional strain, is because we have an enzyme to fix that, DNA ligase. By the way, this is our 7th enzyme of the pantheon. And DNA gyrase, by the way, is part of the termination component. So we only see that one in. So here you can see you've got on the lagging strand, you've got your primase basically laying down the primer. And then here you've had your DNA pol 3, which is already filled in that piece. Now this pol 3 is going to go over here and it's going to basically fill in this piece here. Your pol 1 is now busy removing this RNA primer and replacing it with DNA. And then further on down, your DNA ligase is sealing up these nicks to give you complete sealed up DNA. So when you take a look at continuous versus discontinuous, leading versus lagging, I'm going to draw a line. But what I'm going to do is I'm going to do it in both mechanisms. A continuous line draw is like the leading strand starts at one spot, and then basically it starts and it goes until it stops. In a discontinuous fashion, I'm going to draw the same line, but in this case, what's going to happen is I'm going to do it in chunks. So I'm going to start here and I'm going to connect, but then what I'm going to do is I'm going to go back, re-engage, and then connect this piece, and then I'm going to drop off. I'm going to come back. I'm going to connect this piece. I'm going to drop off. I'm going to come back and then re-engage this piece. Notice at the end, can you tell the difference between the lines? For the most part, no, it's a line, right? But the process by which I got there is different, okay? That's exactly how leading and lagging strand work. So in the replisome, by the way, anytime you see a word like that, things like that, usually what we're referring to is a big complex. And for simplicity's sake, what's happening is we're referring to the complex in a general sense. We're not looking at all the different proteins that are involved in there. Okay. So in the replisome, we have a couple of things, right? So we have what's called the primosome, which are basically focusing on events of initiation. So this is where you have your primase, helicase, your accessory proteins, which are actually your single-stranded binding proteins, and your topoisomerase. All right, so those are your accessory proteins. And then, of course, you have your pol II proper, where you're going to be making your nucleic acid. So this is a big mechanism. This is the whole shooting match. This is everybody all together. A lot of these folks, you know, they're all in place here. Let me kind of point them out to you, and let me introduce you to another character who's very important. So basically ahead, you can see you've got your gyrase, which is like a topoisomerase, which is basically smoothing things out. You can see here, you've got your helicase, which is unwinding things. You've got your single-stranded binding proteins basically here, which are stabilizing that single-stranded template. You can see your pol I is busy replacing the primer with DNA here, and your DNA ligase is over here sealing all those nicks. And then, of course, you have your DNA pol III, which is busy making the actual nucleic acid. Now, there is a new player here that we need to identify. We have our beta clamp, so that's our sliding clamp right there, so we know that one. But this guy right here, the clamp loader, the big squid-looking guy, the clamp loader is like the conductor of everything. So what we just introduced to, these 7 players, are the members of the orchestra. But now we're meeting the conductor who pulls them all together. That's the clamp loader. So the clamp loader is a gigantic protein complex. If you take a look at the clamp loader, it's got touch on every single part of the body. Notice, it is, with one of its tentacles, attached to both DNA pol III. So the pol III is not unguided. It also has connection points to helicase. So helicase is not on its own. It also has a connection to primase. So primase is not on its own. And it's got this big tentacle-like, squid-like area domain called the clamp loader, which will basically actually physically load the clamp onto the appropriate site so that you can actually get polymerase to load. So basically what happens is you load the clamp on there, you load the polymerase to the clamp, and basically the clamp will basically slide the polymerase around. In this case, it's actually sliding in that direction. Okay. Those are the players. Let's see what they're doing mechanistically. Ready? Let's do this. So at first, I'm going to blow this up and try not to write because they get big and blobby. Right? So at first you have your 2 strands. You have your leading strand, your lagging strand. So in this particular case, you got your clamp, which is basically loaded onto DNA pol III on the leading strand, and you're busy going this direction. So the polymerase, as it runs into new template, will remove the single-stranded binding protein and then make a copy of that template. At that point, you're double-stranded, and so it's not a problem. You continue to move through as the helicase opens up new template, and you just basically kind of follow in behind. So that's the easy one, right? On the challenging one, in terms of the lagging strand, let's see what's happening there. So let's see what's happening. So first of all, what's happening is you notice you basically have DNA pol III, which is right here, attached to the clamp loader, and you have an assembled beta clamp, which is then sliding that pol III in its direction of production. You can see you've already filled in a lot of DNA here. It's going to continue the process until it basically hits this new primer up above it, and then it'll stop. Notice behind it, you have primase, who is busy laying down a brand new primer because you've opened up new exposed template that's been stabilized by single-stranded binding proteins. So notice, while DNA pol III is making and filling in a segment, primase is priming the next segment. Now, the next stop. So basically what's happened is primase has finished its job priming, so it falls off. Notice now your clamp loader is still attached to helicase, so that's still basically untwisting the DNA in that direction. Notice here, the DNA pol III is just about done. It's only got 2 more to go here. And then once it gets to that point, what's going to happen is it'll finish and then it'll drop off. So once this finishes, this will basically drop off. And then what it'll do, it'll reassemble at the new primer. So let's go ahead and take a look at its drop off. So the first drop off basically is the clamp loader release. So the clamp releases, which allows the DNA polymerase to release. But notice your DNA polymerase never leaves the clamp loader. It's always hanging onto the clamp loader. So the clamp loader will then grab onto a clamp and it'll reclamp at the new site. So let's go ahead and go to the next image. So you can see the clamp loader has basically changed. It's grabbed onto the clamp. So you can see how that little squid area is grabbed onto the clamp. It assembles the clamp at the new primer, and with its other little tentacle, which never let go of the polymerase, it basically puts the polymerase right there and connects it to the clamp loader. Once you get those connected, then you're ready to start moving down the next segment. And that's exactly what happens. So here you can see you're starting to move down the next segment as you're filling that up. And then what happens? Primase comes in and starts to lay down a new primer on the new exposed template as the helicase continues to move in that direction. Yeah. Well, I mean, it's not necessarily all over the place. I mean, it's not tethered to anything necessarily, but it's not really floating around. I mean, you're not really moving around. There's not really anything to move this around, so to speak. In bacteria, you're just sort of there and you're just kind of rolling through it. So everything else is connected because you're connected to the DNA is connected to you, the clamp loader is connected to everything else. So it's kind of like they're all connected to each other. So they're not really going to be moving around anywhere, unless the clamp loader is moving it, like taking it off and then reassembling it on the new site. Yeah. Oh, it probably messes up a lot, but the problem is that priming site is just going to stay there. It's just going to stay there. I mean, and it's gonna, I mean, until you get it right. So, I mean, but there could be some mistakes in assembly and things like that. You could miss a base pair here and there and things like that. So those are errors of replication. There's lots of errors of replication, but that's the reason why you have that backspace ability, right? Because like, oh, wait a minute, I just totally screwed up the assembly on this one and I kind of missed a couple here or did something wrong here. Then you can just back it up, reassemble, and then the chances of you doing that wrong twice is not likely. So here's everybody in one big table. If you can rattle through this table and explain what every single one of these enzymes is doing, then you're in good shape in terms of the mechanism of replication. Okay, so that's eukaryotes, prokaryotes, right? What about eukaryotes? How do they differ? Well, basically we're different because, well, we don't have circular chromosomes. We have linear chromosomes, right? So that means we have ends to deal with. We also have more DNA than prokaryotes themselves. But basically the replication process is similar. Right? As a matter of fact, as we ask that question, like do eukaryotes do it differently? The answer is, well, we have a lot of similarities. So there's a really strong foundation. Once we understood it in bacteria, there's a really strong foundation in place for us to be able to build our eukaryotic mechanism on top of it. The first difference that we have is origin of replication. Remember, bacteria only had one origin of replication. We have a ton. Not only that, but instead of a fork, what we actually create is a replication bubble. So really what we have is something that looks like this. And actually along a piece of DNA, we'll have like multiple replication bubbles, which makes sense, right? Why would you just use one? Why don't you just get it done faster and do a bunch of these, right? See, these are replication bubbles. Not only that, but unlike bacteria, which had a very specific origin of replication, like a sequence specific version of it, we don't. So we don't have sequence specificity. So these origins of replication can float around. We just do a lot of them, right? So our primases are a little bit different. Not only do we have a RNA polymerase for our primase, but we also have a version that's a DNA polymerase. It's a little bit different. And there's a little bit of difference in the main replication enzyme, right? So our DNA polymerase has a couple of subunits in it that are a little bit different, right? We have a Paul epsilon and a Paul delta, which has very specific functions when we actually take a look at it. So there's some differences in there, but there's a lot of similarities in the basic rundown. So what about the glaring differences? Like, how do you deal with ends? Well, basically the ends of a chromosome are what's referred to as telomeres, and telomeres are protective structures at the ends of chromosomes that protects you and protects the chromosomes from nuclease digestion, right? So you have to have, remember I said the fate of all nucleic acids that are single stranded is digestion. Well, how are you going to protect your ends from getting digested by exonucleases? It's telomeres that do that. But here's the problem with telomeres is that with every generation of mitosis, your telomeres gradually shorten. And so if you didn't have telomeres on your ends of your chromosomes, what happened is your chromosomes would slowly get shorter and shorter and shorter. And eventually you'd start chewing up actual genes that you need. And that would obviously create a genetic train wreck for you. The reason why they shorten is because of the lagging strand. All right, let's take a look at this once you get to an end. So here is your leading strand. This is not a problem here. So remember your lagging strand, which is moving in jerks. Remember the last primer here in line is still not going to be the last of your DNA, right? Because you're going to chew up this primer, and that's what's happened here. But this is going to leave an overhang. But guess what? You don't have a 3' OH to fill that in, right? Why? Because there's no DNA out here. You're at the end. So you don't have anywhere to put an OH. So what happens? That single-stranded piece gets chewed up. So basically, this will get chewed up by exonucleases, and you've got a shorter template after. So if you didn't have something on the ends of your chromosomes protecting them, then your chromosomes would shorten with every round of mitosis, eventually until you have nothing. So how do we deal with this? Well, it's our telomeres, right? So what we do is we put adapters with multiple repeats on the ends of our chromosome. And not only that, but we have a specific enzyme which can self-start. Remember, this is a self-starter. So it has the ability to lay down template from scratch. Why? Because it has an internal RNA template. So it's got its own little template. So all it has to do is just basically lay down an equivalent DNA that resembles its template, and it can do anything it wants. So basically, it just lays down extra repeats at the end of every chromosome over time. And then basically, as you shorten, you just add more repeats. So you keep your chromosome length the same. So really, you're building your telomeres for the purpose of being chewed up. It's like you're giving the hungry dog something to eat. So it's not eating what you really value and prize. As it turns out, telomerase is a really heavily regulated enzyme. It's very developmentally regulated. It's very cell regulated. There is a relationship, a correlation, a direct relationship between cell senescence and telomere length. Why? Because if you lengthen the telomere, the idea is a cell can live longer. That is to say that it can go through multiple rounds of mitosis without degrading. And so as a result, it's a hot target for cancers, right? Remember we said one of the hot targets for cancers is P53. Every cancer cell wants to take the adult out of the room. That's so that they can divide as quickly as possible, as much as they want. But guess what? If you've got a limited size of a telomere, then that means you're not going to be able to divide as much as you want, are you? Because your telomeres are going to shorten, and you're going to basically die because you're not going to be able to last very long. It's like a programmed shelf life, basically. So the common strategy for cancer cells to do is to activate telomerase. What does this do? This extends its ability to do mitosis. We call this immortality. Cancer cells, when they become immortal, basically get themselves in a situation where they can do as many rounds of mitosis as and they'll never die. Why? Because they've mutated or activated telomerase. So they go through a round of mitosis, they extend their telomeres so they can do it again and again and again and again. So this is an abnormal activation of telomerase. Usually it's not this active, but it's a common target for cancer. This is what telomerase looks like. So here you can see this is your internal template, the yellow one. And so you can see then basically all it does, it basically tethers its little adapter to the end of the DNA, and then it just starts to bring in and sort of build out this adapter on the end. And so eventually what you've got is you'll fill this piece in here. You basically have this long telomeric repeat that it just kind of builds out. Okay, last topic of the chapter before we kick into 15 is DNA repair and mutation. I think we'll talk about mutation as well. So DNA repair, right? This is errors of replication. What if we screw it up? Which we can, right? So obviously, if we screw it up, it's an error replication. We have proofreading, the backspace button to fix it for us. But what if it's not just an error replication? What if it's an insult, right? Well, an insult would be caused by what's called a mutagen. Typically, this comes in the form of either radiation or chemicals. And what this does is it increases the level of DNA sequence alteration, which is the definition of a mutation, by the way, above background. Generally speaking, if you radiate yourself, you're going to increase the amount of mutation that you're taking on. If you take a sort of a carcinogen, a chemical that creates cancer or mutagens, then you'll increase your mutation rate above background, and you're more likely to cause mutations. And then, of course, we have all sorts of repair mechanisms that will specifically go in there and repair some of these mutational events or these DNA damage events. So there's a couple of different versions of this. It usually can be broken down into two major categories. The first one is specific, and the second one is non-specific. So specific repairs are targeting a specific kind of DNA damage. So you recognize a particular type of damage. And then in non-specific, you just basically you just look for multiple kinds of lesions, not necessarily specific, just wrong. Doesn't have to be a specific thing that's wrong. And you have both of them at play. So an example of specific repair is what's called photo repair. In this particular case, what happens is when you take on UV light, the UV light is absorbed by your DNA and it creates what's called thymine dimers. So if you have two different thymines that are next to each other, what will happen is they will covalently link between them and create what's called these thymine dimers. Well, that causes a problem in your DNA, right? Because now those are no longer available to pair with your adenines, and we don't know what to do with that, right? So that causes a mutation in that particular area usually. Now in bacteria, they have a way to fix this. They have an enzyme called photolyase. And this is light sensitive. So basically, if it takes in blue light, it'll activate the enzyme. And what it'll do is it'll actually cleave that covalent bond and restore it. Bacteria have this, we don't. So this is what it looks like. So here's your DNA, here's your thymines next to each other. You hit it with UV light and it creates this covalent linkage. Then what happens is the photolyase, which will be activated with blue light, will recognize that anomaly. And then it'll cut that covalent bond and smooth it back out, right? So humans don't have photolyase. So how do we do with thymine dimers? We don't. We live with them. We actually have to sort of create very different recombinational mechanisms and different genetic mechanisms. We talk a little bit about this in the mutation chapter in the genetics class. about how humans deal with these finding dimers. The idea is we never fix the problem. We just kind of manage it and try to keep ourselves functional. A type of non-specific repair is what's called excision repair. Basically, you cut it out, cut out the DNA. First of all, you have to recognize it, right? You have to recognize it as a piece of damaged DNA. Then you remove that damaged reason, and then you resynthesize it, or you lay down the new, right? So that's excision repair. So here you can see you've got a piece of damage. It's recognized by your excision repair complex. In this case, it's UVR. It's a complex of A, B, and C, right? UV for UV replication. And then it'll cut that out. That's the excision part. And then it'll basically smooth that out, lay it all out with the DNA polymerase. Yeah, Melissa. Well, cutting, no. So a damaged liver will regenerate anyway. It doesn't have anything to do with repair. But there's a lot of excision repair going on in the liver because, well, you're eating a lot of toxins and things like that that could cause issues and things like that. But any cell that would be doing mitosis is potentially subject to excision repair. And then of course, another non-specific type of repair is error-free versus error-prone. You don't really see these terms a whole lot in mutationology, if you will. But usually error-free is essentially when you got like a DNA break, like a double strand break. So you have to go and fix that. Right, so that's basically error-free. You're just going to fix the double strand break. Error-prone is when there's a lot of damage. So you're like talking about global damage, big damage. So the problem is you're not likely to fix it all. There's going to be some errors and things of that nature, right? You can't fix it all. Kind of an idea. So that is 14. Felt painful, didn't it? It gets worse. So 15 is actually, wait a minute, did I say that first part out loud? So it actually, 15 is the last chapter. So it's transcription translation. And remember, the key to this is initiation, elongation, termination, right? Those three.
Thursday, what is next week?
The Thursday exam, you mean?
Yeah, sorry.
Yes, it's going to be 12. So it's good. Genetics is going to be in there, right? Because we haven't been tested on genetics yet. So it's going to be 12, 14, and 16. I mean, 15. Does that make sense? Okay. So just to refresh you, because a lot of you guys weren't here, right? I started the day off with some announcements. Lab exam obviously here is in a couple of minutes. I'm going to need a couple of minutes in the lab room itself. You're like, you're good. I got to just make sure everything's set up. So what you can expect is obviously you're going to see some stations set up, and there will obviously be questions there. Remember, it's multiple choice. The stations will be timed. You'll have like 2 minutes, 30 seconds per station. And we'll kind of go through the room sort of in sequence. 2 minutes, 30 seconds will be a long time for some of those. You'll be like just staring off into space for some of those. For some of them, you're just getting started. And that's fine. And there are some stations we're aware of, which are kind of time, they require extra processing time. And for those, they've been duplicated. So you have another round at it. Sometimes that throws students off. So those duplicated ones are there for a reason. It's not a mistake. And so now we're ready to go. And we got a couple minutes. Let's do this. Right. So I just have to do a couple of checks just to make sure that everything's turned on and that sort of thing. So So when we take a look at transcription translation, the first place we want to start is with the idea of the gene, right? And so you notice every chapter is the same, right? We kind of start off with beginnings because a lot of things are happening in parallel at the same time, right? We're all studying different things at different times, looking at different questions. So this is the one where we talked about what is a gene. And we said that there were some people working on flowers, some on corn, some on flies, some on humans. This is one of the human ones, right? So we're going to follow this one up. And so one of these early studies in humans was actually done by Archibald Girard. So remember, this is the time when William Punnett and William Bateson were resurrecting Mendel. They were double checking Mendel's work by recapitulating his experiments in their own systems. Archibald Girard, in this particular case, was actually studying a human disorder. And what he was studying was a metabolic disorder called alkaptonuria. Now, what he did was he noticed a couple of things, first of all. So he knew some things chemically about alkaptonuria. He knew that this was basically enzyme driven. And he also noticed that it had a recessive pattern of inheritance. How did he know that? Because he studied Mendel. Because when he studied Mendel's work, he saw the Mendelian recessive pattern of inheritance, and he noticed that the same pattern of flower color that Mendel was seeing in pea plants, I see the same pattern in my system in alkaptonuria, only it's in patients. So when I talk to this alkaptonuric patient and I collect data on their family, I can see a similar recessive pattern happening in the family. So this is basically the beginning of the way we do human genetics. So he knew biochemically alkaptonuria was a dysfunction of an enzyme. But then you coupled that with this recessive pattern, and now all of a sudden you've got an important link. You've got a patient with a genetic pattern that Mendel was saying that's linked to a particular enzyme, which he knew. So what he did for the first time was make the connection between genes that were recessively inherited and enzymes. Right? And so that's an important linkage that we actually made because we hadn't made that one before, right? So that was something that needed to happen, and it happened actually quite early. So what we're going to do next time then is we're going to pick up with from 1902 with Archibald Girard. We're going to move to Beadle and Tatum, and we're going to start laying some critical landmark experiments down that leads us up to some ideas of how genes actually work themselves. So it's no better place to start than with a nice little history lesson with Beadle and Tatum. So we'll stop there. We'll pick up there on Thursday.